Hello and welcome to Big Ideas Only, and this is a podcast brought to you by Montanus, which is a company where we specialize in producing high quality content for marketing departments in high-tech companies. And I'm your host, I'm Mikkel Svold, and in this episode we are back in space, but not as far as last time where we talked about faraway galaxies and black holes, because I feel like we've barely scratched upon the surface of our own solar system, which is obviously a bit weird because that's a bit closer. So today we're going to talk about our closest neighbors. I said in the beginning, actually, I said 9 planets, but that was wrong, I guess. Mm-hmm. So the 8 planets that gravitate around the sun and all the other things that are in the solar system and that is not also in the solar system. This is going to be super exciting. And to answer these questions, I've invited our expert for today, Mads Fredslund Andersen, into the studio. Welcome, Mads.
Thank you.
And Mads, you're a telescope and satellite manager at the Department of Physics and Astronomy at Aarhus University in Denmark. Did I get that right?
Yes.
Perfect. So I think we should start out by just kind of getting an idea of what you actually do as a telescope and satellite manager. What does that mean?
Yeah. We often have very different titles, and they're not saying too much of what we actually do. So what I mainly do during day is that I'm ensuring that we have telescopes around the world, one in Tenerife, one in China, 3 in Australia, and some others on the way. And I'm trying to make sure that these are operating as good as possible.
And when you say we, is that Aarhus University, or who is that we?
It's Aarhus University and collaborators. So we have partners around the world as well. So that's for the telescopes, where I have been a software developer, also technical engineer, you could say. But some of the telescopes are running robotic. That means that we actually don't do much on the daily operation if things are going smoothly. But if there's problems, or if there's upgrades, if there's stuff we want to add or take away from how we are operated, it's mainly me who does it. And then we have the satellites. So I work on many different projects. For the satellites, we have, for instance, a student CUBE satellite that will be launched in a few years' time.
Is that a full-size satellite, or is that a microsatellite? Because I know Denmark kind of specializes into these micro-satellites.
Yes, it's a small satellite. It's as it is right now, it's not fully confirmed, the design and structure, but it's 10 times 10 times 30 centimeters.
Okay, so it's quite small.
It's quite small, yeah.
And what can you do with that?
Still, we are very ambitious with this mission. It's students who came up with ideas of what we could do, and we could select among the ideas that they proposed. And it's now a collaboration with bioscience, where we want to photograph do images of areas in Greenland where we can then study climate changes just from the images. That could be the melting of ice and glaciers, or the reflectiveness of the ice that tells us a bit about if there's new snow and if it's old and so on.
The satellites that you work with, are they mainly pointing towards Earth, or are they pointing out in space?
This one is pointing towards Earth because it's a bit easier. That's my take on it. If we want to point to stars and do scientific measurements of stars, then we have to be very steady with the satellites. So we will have to have extra things on it, and it grows more expensive and so on. So it takes a bit more effort to build a satellite that can study stars.
And you say that it needs to be more steady, but that's because, like, when you take a binocular and you look at something close by, it's easier to obviously get it within sight.
Yeah, but that's actually a very good comparison, because if you want to, I go hunting sometimes. Mm-hmm. If you want to hit something, you also want your rifle and your binoculars very steady. Mm-hmm. So if you are focusing on something that is far away, you probably have difficulties holding it by hand. Mm-hmm. So you would lean up against something. It's actually the same with the satellite. You want to have a very steady look at it.
Yeah, and the further away it is, the less movement.
Yeah, exactly.
It's like when you play golf, basically. When I play golf, I'm not good at golf. Yeah. Okay, so you're in satellites and telescopes, and are these two things very separated, or do they also combine as a concept?
Well, to me, it combines, because we also work with large NASA missions, satellite missions. Mm-hmm. There we mostly just get the data, but the philosophy of how we want to observe stars can be translated from telescopes to mm-hmm. satellites, and they can, you could say, join forces, so we can use that we are observing from space with the mm-hmm. satellite in combination with telescopes. So it does combine. How we do the project management, you could say, is also fairly similar. Mm-hmm. So there are a few different things, but how the projects develops are the same. Okay,
now let's try. We have some kind of understanding of what you do, I guess. And now let's try to come back to today's topic, because actually in the next episode we're going to talk about more into depth with satellites and telescopes and satellite telescopes and all that. But for today, we want to talk about the solar system. And I think maybe my first question is basically, what is the solar system? Because we've talked about it at the office here before you arrived, and it's always depicted as this closed entity. Mm. So, but what is it actually, and how big is it? And
how big it is actually a very strange, not a strange question. It's an obvious question, but it's not very easy to answer, because we on Earth are 150 million kilometers away from the sun. That's a huge distance. And we are actually close to the sun. So the borders are so far away that we can't really observe them with telescopes nowadays. So there's beyond Pluto and the furthest dwarf planet, there's...
So that was the 9th planet, for those of you who don't... Yeah, okay, so it's not a planet anymore. Yeah. Poor Pluto.
Yeah. But there we have asteroid belts, and also we have something called the Oort Cloud, which is a place where there's it's a junkyard, you could say, leftovers from the early solar system, and stuff that didn't get picked up by planets or didn't fall into the sun. So there's a lot, and we actually don't know really how much there is, but it could extend far beyond what we will ever observe, and
why can't we observe this? Because we can observe stars that are billions of light years away.
Yes, but they shine light. This stuff, like the planets, don't shine much by themselves. So it's only reflecting the solar light, and therefore we can't observe if it's you can't go and see Pluto with your naked eye in the sky,
because it's too dark.
Because it's too far away, so it doesn't reflect much light.
Oh, in that way, yeah. So from here on Earth, standing here, okay.
So that's why we send these probes that goes that do flyby and close encounter with these to understand and check what's going on there. But far beyond Pluto, there's still a lot of stuff. So we can't really see it.
And then how do you define whether it's in the solar system or whether it's outside the solar system? This what do you call it, Oort Cloud? Oort with a T, Oort Cloud?
Yeah. Well, one way of thinking is that it's a gravitational bound to the sun. Mm-hmm. So it's in orbit around the sun. That's one way. But the gravitational pull is said to extend so far away that it's actually halfway in between our closest neighbor star, which is 4 light years away, Proxima Centauri. So that's huge. There's also some other definition of where the borders is where the radiation from the sun matches the amount of cosmic radiation. That's usually what is said to be the boundaries of the solar system. But still, you can have stuff that is bound to the sun by gravity,
even though it's further out.
Yeah. So it's a fairly vague way of defining where it is.
But that also means basically that all the posters that we've seen with the planets on it, and it's a bit misleading, I guess, or I think it's misleading because it does actually somehow symbol or show that it's a closed system that, ends by the 8th planet and then.
Yeah, that's not true, but it's of course for us the most interesting part. It's what closest, so, and we haven't discovered much further out either. So you can also see it as our picture of how it is, because we don't know what's beyond the poster.
And now you said that the border, I'm going to call it, the border of the solar system is defined by either the gravitational pull of the sun versus the gravitational pull of the next sun, which is Proxima Centauri, or is that my something says a sound? Well, that's just my computer, I think. Anyway, so that's one way of defining it, or the radiation.
Mm-hmm.
But how do you measure the radiation out there? How do you know? Because the gravitational pull, I guess, that you can kind of calculate. Can you calculate radiation as well?
No, not well. You can approximately calculate it, but it's actually changing. So it's changing with the solar cycle and other stuff. So we have these very early missions, the Voyager 1 and 2 and Pioneer 10 and 11, I think, and New Horizon, that is traveling away from the sun. And the first ones, Voyager, are already has
it's
already.
A really old one, isn't it?
Yeah, that was in the, I can't remember if it was 70s or even 60s. Oh, yeah,
I
something
think
like
70s,
that. Yeah. But they have passed this radiation zone, so they could measure where it was, and they didn't arrive to that at the same time. So it was at a very different very different. It was at a different distance from the sun when they arrived to this.
Yeah.
So it changes a bit depending on.
Okay.
So that's one of the reasons why it's not very easy to say where the border is, because it depends on the definition.
Yeah. One thing we did also talk about before the episode was what is, when you're not counting the planets and you're not counting this Oort Cloud, what is in space? Is it the same, like, is space itself, is that the same, a couple of 100 kilometers out from Earth? Is that the same material, or whatever you call it, non-material, I guess, as 100 light years away? Is that the same space?
Yes, it's very empty.
It's just a big nothing.
It's pretty much big nothing, yeah.
That is very fascinating, isn't it?
There's of course light from stars and cosmic radiation and so on, but there's really not much. It's really empty.
I find that quite fascinating, that we can explore something that is relatively close, or very close in space terms, I guess, very close, and then it's the same as basically everywhere else.
That's how we understand it, at least.
Yeah, I find that very fascinating, and I want to talk about also, what do you think, from looking at the solar system, why is that interesting for you to look at? What is interesting about the solar system?
Well, the main thing is that it's very close. Everything in the solar system compared to other stellar systems, star systems, is very close. So we can send these missions that will actually go and investigate, where we can do, like on Mars, where we can have samples, do samples and check stuff, check our theories in much more detail than we can around other stars. So and of course it's the basic, everything, all the theories we develop, and both about the sun or about how the solar system came to be in the first place, comes from our visual observations of how the solar system is. that we can then go and check on other systems when we started in 1995 finding other planets around other stars. But before then, we actually didn't know if the solar system was unique, was one of a kind, or if it was a common system.
And is it a common system?
Yeah, it's not too strange. The sun is a very common star, and the sizes of the planets, and we know that most stars has planets and more than one, so it's not that special, sadly.
Yeah, that's kind of sad. But is there something that is different from the sun or the solar system in terms of what planets are there compared to what we know from other systems?
Well,
obviously we have life on one of them.
Yeah.
And we don't actually know whether other.
Yeah, not yet.
Not yet.
So before we started up finding planets around other stars, we had a theory of how the solar system came to be, and why we had 4 rocky planets closer to the sun and gas planets more distant from the sun, which is because you could have ice on solid form in the outer regions, where you could then build up bigger planets that could hold an atmosphere like the gas giants has.
But are they still with solid ice, or?
The cores are so compact that it's maybe not solid ice as what you put in your drinks here, but it's on a different form. But it has a lot of the components.
But they are solid, though.
Actually, it's interesting you ask, because it's not easy to check. How we can't send a space probe into one of these planets and then take a sample and tell us. So it's theories, but there might be some sort of solid surface beneath the atmosphere, but it getting very compressed, so it's different kinds of surface than we know from the Earth, for instance.
Actually, I know this is a kind of a segue, but one of the things that baffled me quite a lot is, how do we know what's inside Earth? Because we've only dug 100 meters into Earth anyway, or a few kilometers maybe.
Yeah.
But how do we know what's inside?
We actually we come
it's kind
with
of the same problem, isn't it?
Yeah, and it's actually a good point, because some of the theories of what's inside comes from earthquakes. So it's these earthquakes start shaking the whole Earth, and depending on what's inside, the waves that are being excited will tell us a bit of. So it will travel differently depending on what's inside.
Sound waves, or what kind of
sound waves inside? Yeah, inside the Earth.
Okay.
So it's maybe a different sound, but it propagates as sound waves, but it's in a different material. So and depending on the material and the composition, it will then move differently. And then you can measure. And
in the pictures that I've seen, where Earth is cut in half, and you can kind of see the fireball in the middle and all these layers. How do you know that they're layers? That it's not just one big, the same?
Yeah. So that's. I'm not a geologist, so I don't know too much about it. But it is from these waves that you could measure, and how deep they go, and so on. And if you can measure that they change in structure depending on how deeply they went, you can see, okay, something is going on from this depth, and so on. And then it's we are expecting there is a liquid core, because we have to have something that can rotate and generate our magnetic field. So there are theories of how the Earth's composition is based on what we can measure and what we can then come up with of ideas.
Okay, I'm just going to try to kill this sound that keeps coming up. And now, this is how we know something about what's inside Earth, or have theories about that. But And you say that we measure that by basically listening to sound waves, so looking at sound waves, and I guess a lot of other tools as well. But then, how do you do that on planets outside Earth? How do you then know what's inside? Because you, as you said, you can't send a probe. And I guess you can't listen to sound waves as well.
Good question. And actually, even objects, other planets in the solar system, we don't know much about.
Okay.
So we have theories of what has to be inside based on, we can measure their mass and their sizes and so on. So we can come up with a rough estimate of how they are supposed to be. But not many have we actually tried measuring what's inside. And on Mars, I know there's a seismograph, so what they try to do the same on Mars as they do on Earth, measuring these waves to tell what's inside.
So they've actually put a seismograph on Mars?
Yeah.
Okay.
I'm not sure. Maybe they also did it on Venus. I'm not sure.
But why is that's another question. Why is it important to know what's inside the planet? I guess it's important to know what's in the outer layer, because if there's water or something, blah blah blah. But why is it important to know what the core is? There's nothing in there.
There's a lot of what I do, which is just nice to know. So many things is just our perception of the universe. It's mostly just nice to know. So we want to build a better and better understanding of the whole universe, and understanding our neighborhood in the first place is a good starting point.
Why do we want to understand the universe?
Well, I find it interesting, at least, and I think since you're doing these podcasts, I think you do as well.
That's true. Point taken. I'm just trying to provoke a little bit. No, I think I often find that like basic research is the most interesting, because it's also where you find where you can really leap, because you really don't know a lot. So even small details, they'll kind of lift you to a new understanding of a lot. You just briefly said, mentioned how the solar system has come to be. How did it actually?
Yeah, I didn't say much.
You just mentioned it, and I noted it. And I was like, I gotta ask for this.
Yes.
So how did it come to be?
Yeah. So before the solar system was even there was a gas cloud. That's the common theory. A gas cloud that got perturbed by something, which meant that you could have contractions in some places and less matter in some other places. And then gravity started to kick in and made more stuff fall towards a center. Mm-hmm. And this made the gas cloud started rotating. And during this project, matter...
why does that happen, the rotation? That's not obvious to me.
No, and I can't really remember if it's momentum conservation or something like that. So you have a physical explanation of why that has to be. And then the stuff fell in towards the center, and it could combine to bigger grains of dust or ice, because mostly it's hydrogen and helium that the whole universe consists of, and also the starting point for the solar system. And as more and more built up, of course, you got the star in the center, the sun, but other stuff would then rotate so quickly that it could, like the moon around Earth, or the Earth around the sun, it would not fall into, but fall just in the right speed that it would match the gravitational pull. And that
so the forces of the rotation around, like when you spin a wheel around, so I don't know what that's called in English, but the force of going around equals out the gravitation of the sun.
Yeah, so
the outward pull equals the inward pull.
Yeah.
Okay.
And some stuff piled up and made planets, and did never fall into the sun, but most of the stuff, it's 99.9% of the whole material in the solar system is in the sun.
Okay.
But the rest, which is not a lot, but it's still the planets and the comets, asteroids, moons, etc. But that's our theory of how it started. But these theories, of course, we cannot go back in time to check it. So what we do is checking against exoplanets around other stars, and seeing if we can see similarities of very early planetary systems there that resembles what we thought was.
And how do you know it's an early planetary system when you look out?
There are some ways of measuring age. For instance, if we can measure the amount of hydrogen that has turned to helium, so the fractional difference in the star, then we can say something about how much time it has taken for it to fusion these hydrogen into helium.
Okay, that's a bit of a sidetrack, I can hear. but I was wondering now, looking from Earth and being a bit selfish about it, how does the rest of the solar system kind of keep Earth, or how does that? Because I know that some of the planets, they kind of protect Earth, but how does that work?
Yeah, so Jupiter, the largest of the planets in the solar system, is somehow protecting against inward coming asteroids and comets and so on, because its gravity is much bigger than Earth, for instance. So it can diverge stuff. But the main protection is coming maybe from the way it's, as we said in the early part, there's not much. So the only stuff that comes in is small dust grains that makes the meteors we see on the sky, and some are a bit bigger. They will not be too damaging. Okay. Then we have, of course, the cosmic radiation, where our atmosphere protects us, and there's also the solar wind and particles from the sun that we need protection from. So that we have to put on sunscreens because the UV from the sun can be damaging, and there we have the atmosphere that protects us. But the planets, it's mostly to redirect larger objects.
And does that mean that the planets rotate in the same, not the same pace, but they rotate like next to each other, parallel to each other? Because otherwise we would be at one side of the sun and Jupiter will be at the other side of the sun.
That will happen, yeah.
Okay.
Yeah, so we're not holding hands in the solar system. We travel at different. So for the Earth, it takes 1 year to travel around the sun. For Venus and Mercury, it takes less. For the outer planets, it takes longer. So it's we will catch up on the outer planets, and the inner planets will go around faster than we do.
Mm-hmm. Okay. That's kind of interesting, I think. Now, we've established kind of quite a lot about the solar system now, I think. And now I think just our time is flying also, I can see. But just before we end, I want to kind of touch upon what kind of tools do we use today in order to understand the solar system. So we started out by talking about telescopes and satellites, but how does that help you, basically? Is the telescope, is that just a big pair of binoculars, or?
Yeah, in principle it is, but in the solar system, things are so close that of course, early on we did use binoculars also to understand our solar system. Now it's mainly sending missions to do deep investigation of several planets. Mm-hmm. So we have had missions to almost all the planets. Not all of them we have touched ground, but because of, for instance, the gas giants, we can't.
Yeah, there's no ground.
But we have had dedicated missions to go to almost all of them.
Okay.
Some of them were flybys where you could photograph and do some simple measurements, or not necessarily simple, but some measurements from the probe. But But others, for instance, on Mars, we send a lot. These Mars rovers to do dig into the dirt and try several, also sending to several different places on Mars' surface to see how it has evolved. You can study. By studying what you see and what you can measure, you can tell a story of how Mars was in the past as well. So that will tell us a lot about how the solar system has developed throughout time.
Okay. A question just sprang to mind. Are we absolutely certain that there are only 8 planets? Or could we also have not found one yet?
It's actually one of the reasons why Pluto was sadly degraded to being a dwarf planet was that we started finding new objects that were similar in size to Pluto, further away. So we would then not. Everyone was taught we had 9 planets, but then the whole story had to change, and we didn't know if it would have to change once or maybe a number of times, and we couldn't really see how many planets we would then find further on. So there were a new definition, and the definition was that, of course, it had to be in orbit around the sun. It had to be round by gravity, and it had to not produce light, so it could not fuse hydrogen to helium in its core. And then it had to have cleaned its orbit. And that's the one.
Yeah, what does that mean?
Yes, that's the one that caused Pluto to be degraded, because it's sitting at the edge of the Kuiper belt, which is an asteroid belt just beyond Pluto. Okay. So that means that there's a lot of stuff there, but in the orbit it has a bit of an eccentric orbit. So part of it will go into this Kuiper belt and part just outside. So it hadn't cleaned away all the material that is in the same area as itself.
Okay.
All the other planets have
so
cleaned.
It's not a clean path, basically.
Yeah.
Yeah.
All the other planets have done that. So and then further on, these extra objects that were found further away were also in the Kuiper belt. So that's why.
So, how many dwarf planets have we found?
Oh, I actually don't know the number, but there are.
So it's many, in other words. Or
not many, but there are at least 5 or 6, and maybe a few more. There's only one that is fairly close to us, so that's in the asteroid belt between Mars and Jupiter, which is called Ceres. Okay. And then further away, at the distance of Pluto and even beyond, there's a few more. Makemake.
Is Ceres, is that smaller than Pluto, or why do we know Pluto and not Ceres? Because Ceres is closer.
Yeah, it's smaller. Yeah.
Okay, so we actually just hadn't seen it at that point.
Yeah, and maybe we had, but the redefinition then made it maybe also come up into this group of a dwarf planet instead of being just an asteroid.
Okay, yeah, that also makes sense. Okay, now our time is actually up, but I want to just, the last question is, I want to know what you're looking forward to exploring in the near future in terms of the solar system. And then afterwards, I want to know where listeners can find out what you do if they want to follow what you do and what you're working on. So what are you looking forward to first?
I hope in my lifetime that we will have manned mission to Mars. That will be amazing.
And is that within reach? Because now I'm not talking to Elon Musk.
I think it is, but it's of course there's a lot of politics and so on into that one as well. But I have a feeling that it will happen in my lifetime. So that's something I really look forward to see. Also, there is some of the moons around some of the bigger planets. Jupiter and Saturn has a lot of moons, and some of them are ice moons, where it would be really interesting to see if there's anything underneath the ice. So missions to those would also be
landing something on those moons.
Yeah.
Okay, yeah, that does sound exciting. And now, where can listeners find out more about what you do and follow some of your research if they want to?
So I try to keep my webpage on our university webpage fairly updated, so most of the stuff is there.
Perfect, and we'll definitely link to that in the show notes. And our time is now up, so Mads Fredslund Andersen, thank you so much for coming.
You're welcome.
And I look forward to talking to you again in the next episode, where we'll touch upon the more of the equipment side of exploring the universe. And now to you, dear listener, if you do like this podcast, please help us by subscribing to it, and also, of course, share it with your friends and family or whoever could be interested. And you can find all the links to all the stuff that we've talked about. You can find links to that in the show notes on our website, which is montanus.co, and that's CO without the M. So it's montanus.co/big ideas only. And that's it for now. Thank you so much for listening.